Hello everyone, welcome to this talk about DFT+U+V method. My name is Wejdan Beida. I'm a PhD student at the PGI1. I will talk about the implementation and basic usage of DFT+U+V method in Fleur code. So let's start with why we need DFT+U+V method. As you learned in previous talk, density functional theory tend to underestimate interactions in systems with localized electrons. This leads to an inaccurate description of systems, of such systems, especially the electronic structure and magnetic properties. A notable example is type 2 antiferromagnetic nickel oxide. It is rhombohedral cubic rock salt structure. Here I present the DFT density of state, emphasizing the D character of the nickel atom up and atom down in black and red. And also we highlight the P character of the oxygen orbitals. You can see that the DFT has a small gap and it is about 0.6 eV. And this is smaller than the experimental value, which is about 3 eV. Also, you can see that the dominant character at the top of the valence band is d orbitals of the nickel, where experiment says that it should be the p orbitals of the oxygen. Similarly, DFT incorrectly predicts the lowest part of the valence band to be dominated by the p orbitals of the oxygen, while it should be the nickel d characters. By introducing a Hubbard U correction on both nickel and oxygen, we add a U of around 9 eV on the nickel and U of 6 eV on the oxygen. One can observe a significant improvement in the band gap size. And actually, it is in the experimental range. Also, the dominant character at the top of the valence band is P, as experiment says. Also, the dominant at the lowest part of the valence band is D of nickel and not P of oxygen, as DFT says. However, we can see that adding the U lets the lattice to expand, and this contradicts experimental result. So to address this, we aim to correct by including the nickel-oxygen, oxygen-oxygen, nickel-nickel interactions. These types of interactions, which they are long range, between atoms cannot be captured by the on-site interaction U. Accounting for them is crucial when we study systems which they are in low dimension as two-dimensional systems, also in charge transfer insulator and complex magnetic orders as spin density waves. Our approach to overcome this limitation is by extending the on-site Hubbard model to incorporate interaction between electrons on different atomic sites. So now our extended Hubbard model have three terms. The first is the hopping of an electron from a site to another. And we have the Coulomb repulsion of having two electrons at the same site. Also, we include the interaction between two electrons on two different sites. How do we achieve this? Electrons, which they are not involved in strong correlations, are treated using DFT, standard DFT, while only correlated electrons are handled via the Hubbard model. Since these correlated electrons are already handled or treated in DFT, then we subtract a term to account for double counting. I will discuss this concept in more detail later, but here we have the energy term responsible for the on-site interaction, and this is for the inter-site interaction, and this is introduced from the paper of Campo and Cuccioli. Now we come to the question, how is this implemented in flow code? In DFT+U approach, you were introduced to the concept of on-site density matrix. With the addition of the plus V, we now need to define the inter-site occupation matrix, and this quantifies how the electronic orbitals of atom I interact or correlate with orbitals of atom J. Mathematically, the inter-site occupation matrix is defined as the sum over all k points and bands of the product of the Kohn-Sham wave function projected on the local basis function of atom J. This quantity we multiply by a similar one, but it is projected on atom I. We have this form for the inter-site occupation matrix, and in Fleur code, we divide our space into two parts. The first is the muffin tins, which they are around the atoms, spheres around the atoms, and the region in between muffin tins is the interstitial region. And a Kohn-Sham wave function in FLAPW bases is expanded in the interstitial region as plane waves, while in the muffin tins, they are product of either the radial function or the energy derivative of the radial function multiplied by the spherical harmonics. This you have encountered before with in other talks. And for the choice of the projector here between atom J and atom I, we chose either the multiplication of the radial function or the energy derivative of the radial function by the spherical harmonic at atom I and J. With this implemented in Fleur, we have a large matrix. On the diagonal, we have the on-site density matrices, and on the off-diagonal, we have the inter-site density matrices. Now, the second step is to implement the potential term, which is responsible for the inter-site interaction. You are already familiar with the on-site energy Hubbard term and double counting term. It's double counting term. Now I will introduce the Hubbard energy term, which is responsible for the V, and in the plus V, we took only the double counting, which is in the full localized limit. So it is either fully present or fully absent. After applying the necessary subtraction of these two terms, the Hubbard and the double counting, to avoid any double counted term, we obtain the energy term of V, which is mainly the trace of the multiplication of the two inter-site matrices, and we have this object V. This V quantifies the strength of the interaction between atom I and atom J. To determine this parameter or this value, we perform a constrained random phase approximation calculation using specs code, as you heard from Dr. Friedrich talk. Now we have the inter-site occupation matrix, we have the inter-site potential, and we have the inter-site density matrix and the energy. we want to calculate the potential. It is calculated similarly to the Kohn-Sham approach by taking the functional derivative of the energy term with respect to the inter-site occupation matrix. And the system is then, in the previous iteration, the system is then solved in a self-consistent cycle, solving this eigenvalue problem, recalculating the density, the inter-site occupation density, and also the potential, repeating this process until convergence is achieved. Now, let's answer the question how to perform DFT+V calculation in Fleur code, because you already know how to add the +U in the Fleur code. So for the input side, let's assume that we have a system with two atom types. Here it's our first unit cell. It has atom 1 in red and atom 2 in green. Atom 1 can interact with four green atoms on the level of nearest neighbor. In the input.xml file, you add such an input. Here you specify the reference atom, the index of the reference atom, which is 1, and then the index of the other atom, which they are 2. Also, you should specify the orbital character of the reference atom and the orbital character of the other atom. This can take value 0, 1, 2, 3, or 2 or 3. And so here we have 1, 1, which means PP interaction. Since all four atoms, these 4 atoms are equidistant from atom 1, and they share the same orbital character, then the parameter V for all of them is the same. And here we specify it in EV. Now we are left with specifying the position of these 4 atoms. And for each atom, or for each green atom, we need to specify its position by providing the integer multiples of the unit cell basis vector in the x, y, z directions. This represents the shift of the atom relative to its equivalent in the first unit cell. So we say that in the first unit cell, we have this 2A atom, and we would like to know how this 2B atom is shifted from 2A atom. And these, the integer numbers multiplied by the unit cell basis vector, which they are represented here. As an output, you would get an NIJ MMP out file, a 7x7 block, each for a specific spin per index and atom 1, atom 2 indices. In the out file, you can have a look at the distances between the pair atoms. So, for example, the distance between atom 1 and this atom, or this or this. You can have the distances by looking at this line, and also you can look at the convergence of the inter-site occupation matrix. Now, let me return to the example of nickel oxide. We construct a model that includes the nickel d orbitals and the p orbitals of the oxygen. The Foldt-Hubbard matrix obtained after performing constrained random phase approximation is structured as follows. On the diagonal, we have the on-site U, this is on the nickel, and these are on top of the oxygen. And on the off diagonal, we have, for example, the interaction between nickel 1 and nickel 2, the interaction between nickel 1 and oxygen 1, nickel 1 and oxygen 2, and so on. So we put all these interaction into our DFT+U+V calculation, and we perform this calculation, and out of it, we have the density of state. Here, one can observe that the improvement which are already introduced by DFT+U are still present in DFT+U+V, but with a slightly larger band gap. Additionally, the cell is contracted again, and this is closer to experiment. So with this, I come to my conclusions, and I would like to thank you for your attention.